Hello, welcome. This is an A2 Edexcel maths video for C4. Now, in this video, what we're going to be going over is I'll just be recapping what we've done previously in vectors, and then I'm going to be extending the theory a little bit more so you can have a bit more maths excitement, as it were. So, really, to make you that little bit more hateful of me, what I'm going to be putting you through is I'm going to be putting you through what is an equation, a vector equation of a line. I'll be talking you through how to find the angle between two vector lines. Now I've sort of done something quite similar to that before, but that was with two vectors. These are with two line vectors, totally different thing. For what we're concerned, we're totally different. To make it nice and easy for you to understand. So that's essentially, and then obviously you should know this. Obviously after that, we're going to be going through parallel lines, parallel vector lines. Now that last one, the other two are more complicated, are less complicated than they sound, whereas that one I think is actually more complicated than it sounds. So, you know, a nice little end treat there for you. So, it's alright today. I mean, you know, it's not this fairly difficult lesson, but, you know, it's maths. So, maths is awkward. So what I'm going to do, as I said, is I'm just going to go through what we've done in the past few videos, so I'll kick off with that. So, the types of vectors that we know so far. So I'll do a nice recap on the board. So you can skip the next minute or so if you're not interested in this. But I think it's a good way to think about it. So I'll just put a thing with vectors. Somebody doing half your revision for you? Okay, so now the types of vectors. So this is the very first thing that we looked at. Now, there was a standard one where you had something like this, where it's an arrow and it said 3 newtons. And we talked about the difference between scalars and vectors, and we said a scalar just had magnitude, whereas a vector, standard vector, all vectors have magnitude and direction, such as that. We also talked about the column vector, where you had 3 minus 2, so it was right on the top one was plus, left was minus, and then on the bottom one, if it was positive it would go up, and if it was negative it would go down. And then we talked about the other type of vectors. So we talked about unit base vectors, a vector that has a magnitude of 1. So I'll just put something like a 1 newton. We talked about 3D unit base vectors. Now to understand 3D unit base vectors, we need to go back to our idea of what a unit base vector is. Now we said it's a magnitude of 1 in a given direction, but we said the x-axis, we said the vector that was in the x-axis now the magnitude of 1, we call that the letter I. In the y-axis we had a vector and we called that j. So in the z-axis we had a vector and we called that ijk, so we call that k. So that's sort of gone over 3D unit base vectors as well. So as I said, quick recap. And then after that we went on to looking at the length of 2D and 3D vectors. So when we had a 2D vector, something like this, so it's very simple, just use Pythagoras. So that's 3 newtons, 4 newtons. We had something like a resultant force, for those people doing physics, and it was the square root of 4 squared plus 3 squared equals the square root of 16 plus 9, which is square root of 25, which is 5. So that was a 2D unit base vector. The idea of 3D unit base vectors, finding the magnitude. So this R is actually denoted in maths by this. So that is essentially that. So it looks like the modulus bit, and it is essentially because you would never have a negative length. But that's obvious, but that's just for people who are a bit thick. And don't realise you can't have a negative length. So if you're one of them people, you know, moderately intelligent, but you're all still thick enough to be able to listen to me, which I probably think that's quite thick because I'm not the smartest kid in the world. Well, that's like insulting my audience, so never mind. Hopefully I don't punch the producer. I'd end up punching myself, so that wouldn't be too good. So anyway, we're going back to this math stuff that we're going to be doing. So that's how we worked out to 2D. The theory for the 3D one is exactly the same. So you just do the square root of, say if it was, you wanted to find the length of A, and you said the vector A was equal to 3i plus 2j plus 6k. Remember, don't forget the little asterisks, not asterisks, the squiggly thing. So it was 3 squared plus 2 squared plus 6 squared, and that's equal to the square root of 9 plus 4 plus 36, which is square root of 49, which is of course 7. Did that in my head, that's pretty good. Yeah, then we said the angles between lines, so that was a little bit more complicated. So I think I'm even going to go to a different colour for this. It's crazy. So for this we said the angle between two lines, and it's always the angle that's going away. So this was 3i plus 2j. Obviously it's not because it's a 2D one. It's more of a... Anyway, just imagine it is. And that was... That was, let's say, 2i plus 6j. And we said we wanted to work out the angle this. No, it's not 90 as it looks, I'm just doing it for demonstration purposes. We said the cos theta was equal to vector A times vector B of the modulus of A, the length of A, times the magnitude of B, the length of B. Now AB, we said, if you remember, was equal to A1, B1 plus C1, plus A2, B2, etc. That was just a recap, really. As I said, I didn't go into too much detail because there is another video, and I was just to get your mind thinking of where we're up to so far. So if you can't remember, because I'm sure I make up a mess with these videos of the way they're uploaded. So I'm assuming that's what you know. As I said, it's a quick recap, so there's a proper video on that if you want to watch it, if you want to put yourself through that. But as I said, hopefully, it's fairly standard stuff that. We're just going to be taking it a little bit further today. Okay, so the first thing that's on my agenda is to talk about the equation of a vector line. Now, the closest thing that we'll have done to an equation of a line, well, we've got to say, not this thing. Way back in C1 we did something like this, where it was y equals mx plus c. And we formed that equation because we said, okay, well we've got a y-axis here, we've got an x-axis here, and say it went through like 3, and it had a gradient of 2, that we said y equals 2x plus 3. Okay, so that was obvious, really. As I said, that's the basic maths. But how can we apply something like this, the equation of a line, to an equation of a vector? Okay, so it's going to obviously be a little bit more intense because we're in C4 now. We're quite intelligent. We're not doing C1. Well, it's a shame because I'm redoing it. Never mind. Just because I want to get 100%. Got 99.9678% last time. So, that 0.0000257 mark. Oh, it's just right. It's probably they saw my name. Like we're going to deduct him a mark already just for having a name. Just being an idiot, to be honest. We don't like him. We've seen his YouTube videos. He's a bit of a pleb, so we'll deduct him 5 marks. Anyway, so some maths coming on to now. So we're going to talk about the equation of a line for a vector. Okay. So let's just find an example. Okay, yes we go. Right, so I'm going to draw a pair of axes. Sorry, I've actually put an example on the last page of this little document I've got here. So, just to confuse everyone. So say we've got some axes that look like this. We've got a standard y-axis, standard x-axis like this. And we've got some vector equation. We've got some equation of a line here. We'll say it goes through, this isn't really relevant to be honest, say it goes through 3 x on the y-axis and goes through the x-axis at 4. Now we could come up with a proper equation of a line there, but we're more interested in this equation of the vector. Okay, so this is the origin, obviously, right here. So it's got the coordinates 0, 0, or we denote by just 0 as the origin. And then we're going to get a vector. We'll call this A. So we'll be upside down. We'll call this the vector A. Right, and we'll say that A has the coordinates in terms of unit base vectors, or the column vector. We'll say that's minus 2, 4. Okay. Okay, so that's what we'll call it. And then obviously this one from A to 3. So this will have a we'll call this the vector. Well, we're not actually not going to give it a name, but we'll just to the distance. So because that's 2, 4. My whiteboard skills are terrible. So it's 2 to the left and 4 up. So you could say it's minus 2, 4 in terms of x and y coordinates. So therefore this will be 2 minus 1, because it's 2 to the right and down by 1 to get from minus 2, 4 to 3, 0. That's the vector there. So basically, if we add this vector, whichever way we want to go, if we keep moving this vector along, we're always going to be on this line. Kind of logic, really. Just following the same line. It's going to have the same gradient, so it's always going to be, no matter how far down we go, if you just counter out my terrible art skills, we're going to have some kind. It's going to be parallel to the line all the way down. So no matter what we do, it's always going to be on that line. So if we assume all these are the same length, obviously they're not going to be, because my drawing is absolutely terrible. So it's not proportional. It's not going to be. It might not be 2 here, and it might not be 2 over here. It's just a representation of rubbish drawing. So say we want to work out. Say if we're on this one and want to work out what R1 is. So that R is a vector. That's R1. Okay. We've got the standard. So this vector B here. This vector A. Call that A. We say that the vector A, because it's got the coordinates minus 2, 4 in terms of the column vector. So the column vector, so therefore the R1 is going to equal minus 2, 4. However, because this is the A, so when we do minus 2, 4, we get to A. But say we want to get to this point over here. So we've already gone up minus 2. So we followed the vector minus 2, 4. That's got us to A. So therefore we can say 0 to A is equal to minus 2, 4. Okay? Because that's all we've got to that point here. We're at that point. Okay, we want to get to this point. This is starting to look really weird, this line. But think of it what you want. So say we want to get to that point there. The end point of R2, where the R1 meets the this line here. So what do we do? Well, we're going back to. So we're going back along. So actually, this is bad, really bad. So yeah, the vector is actually going. Vector is actually all going down. So they're all going down this way. Shouldn't have drawn 2 arrowheads on them. So they're all pointing this way. So all the vectors are going down. So because all the vectors are going this way, downhill, and we want to go uphill, we're going to have to do the minus of the vector. Because we're still going in the same, we're going along the same length, but we're just going in the opposite direction because we're rebellious kids. That's obviously why you're watching my videos. So if we go back 2, we have to go back 2 of these. Now, we're not just going back 2 of anything. We know what each one of these are. So we're going minus 2 times 2 minus 1, because 2 minus 1 is the column vector for each of these parallel vectors. So if we work this out, therefore R1 is equal to minus 2 over 4. Take times 2 by 2, that gets 2 by 2. 4 minus 2. So that's the equation for R2. So for R1, sorry. So you work that out. So you do the tops take the tops and the bottoms take the bottoms. So this would be 2i minus 2i 4j, and then it'd be so minus 2i minus 4j and minus minus 2i minus 4i and then plus 4j minus 2j. So therefore we take away the tops, take away the bottoms. So therefore that gets us minus 6i and plus 6j. Therefore that's what we can say. That is equal to O to, we'll call this point Q. So O to Q is equal to minus 6i 6j. Okay, and that's just because we've gone backwards 2 of these vectors, and we've got to this point now. Looks something a lot weirder than what it should be, but it's maths, it's pretty weird. So anyway, we've gone back 2 of these vectors, and we've just used a constant vector. Now we could do this, apply this principle to something else. So if we wanted to get from over here, so if we wanted to go to the right by 3 of these vectors, so if we called this one, going out of colours, that's the end of that pen. So we want to get to R2 over here. Okay, so therefore R2 is equal, we're still going to have to be at this point A here. We're going to have to be at this point A. And we said O to A is minus 2, 4, so we're going to keep that. So minus 2, 4, because that gets us on the idea of this line. But we're going right, we're following this downward curve. So we're adding it this time, not taking away, because we're not going back up the curve being rebellious kids. We're following the grain, and we're going right, so we're adding it. We're following the vectors essentially. So we've gone down 1, 2, 3. We've gone down 3 vectors. It's like going back a primary school list, but never mind. So you add 3 lots of each one of these vectors. Now we know each one of these blue vectors is 2 minus 1, so we're going to do the same thing over here. So therefore R2, vector R2, minus 2, 4, plus times tops, so 3 times 2 is 6, 3 times minus 1, minus 3. Sort these out, so you take the tops, take the bottoms, so minus 2 minus 2 plus 6, that's 4i, minus 2i plus 6i, positive 4i, 4 plus minus 3, so it's 4 take 3 obviously, so that's 4, that's 1j, so that's just j, or 1j, so therefore that is a coordinate of O to, we'll call this k, so O to k is 4i 1j. Okay? Because what we've done here is we've said, okay, this is the starting value, this is 3 lots of these vectors going down. But we should be starting to spot some kind of a pattern here. Now if you refer it to this idea of y equals mx plus c, because this is essentially what the same thing is, but we just talk about it in vector style. If we relate this to something that we've done, so we may want to rewrite this as y equals c plus mx. Because that is more looking like what we've got down here where we had r1 equals the starting value, add or take however many we're going down. Because the gradient is negative really. Oh, sorry. Keep catching the same edge. Anyway. So the gradient, so this is sort of representing the gradient because it's, well, you sort of think of it like that. It's more to do with how many magnitudes. So this m, actually, instead of representing the gradient like it normally does in C1, because we're in C4, we can imagine this representing the magnitude for m. It's good that it's probably like been that all along, and we just never got told that. Because you never get told stuff. You always get told a roundabout way, but it's never correct. Because, penny for life, where people, live their life like that, just telling rubbish. So anyway, this is m is the magnitude of this line, because for each sort of vector we add. So if we were to do R3 and we wanted to add another vector on, so we does R3, it'd be R3 is equal to the same starting point, because we're starting from here, which is minus 2, 4, plus 3, because we're going to another one, 3 plus 1 is 4, 4 times 2 minus 1, and you'd expand that out like we did before. This m is the magnitude, essentially. Okay, and this R1 is basically, this is no longer the y coordinate, we can't really think of it like this. This R1 is essentially the length, what we want to find out. This y is the solution, really, in the case of this. And this mx is more related to that there. And then this c is, it's not really the y-intercept, because it isn't, but you can think of this c now, as in context of this, as the starting vector that doesn't change, because in C1, C doesn't change. You can't really change C. The gradient you can change at different points if it's a curve, but as I said, it's a straight line thing, sort of. So basically, if we relate this to vectors, how can we state each of these points in terms of vectors? Well, this y is going to be what you're trying to find out. This y's solution. It's not really the y coordinate, because it's not C1. So you can. I'll explain a different way of thinking about it as well. But this might work for you. It works for me. This C is, as it is. C is actually a constant. We call it constant, but we don't really say that in C1. C is a constant. We say it's a y-intercept, but it is. But in this case, it isn't. It's just a constant, and that's because we always have this vector that we start from here. So we always have this constant vector. In each of these calculations, you always see the start minus 2, 4, minus 2, 4, minus 2, 4. So this C is constant, it doesn't change. However, this mx, the gradient, does. So m changes, this magnitude changes, because m isn't the gradient in C4, in this case, in vectors. We're thinking of it as the magnitude. And the magnitude is, when we said the unit-based vector of 1, you can think of these as unit-based vectors, just in a roundabout way. So these have a magnitude, each of a magnitude, but yeah, so if each, it depends how you think about it really, but if we have a magnitude of 6, we have 6 of these, so we have a magnitude of 6, then we have 6 lots of this. So this essentially is the x, because that's the sort of each addition as we're going in the x direction, if you think of it like that. Okay, so the m's the magnitude. That's how you can think of it, but another way of mathematical way, and the way you should probably think about it in the exam, but as I said, that was just a nice way I think of thinking about it. Just rub this stupid maths off the board. Didn't say that. What the actual equation of the line says, it says r is equal to a vector a plus lambda vector b. I think that makes a lot more sense, but whatever. So I'll explain this one as well. Now this r is the vector, so vector r1, vector r2, vector r3. It's just the length. This a is the starting vector that you're given. So in the case that we had, it was minus 2, 4 as a column vector. This lambda is again the magnitude. As you can see how this is quite closely related to this. We have y as being r, c as being a, and mx as being lambda b. That's how I think of it. So you can see how they're related now. Probably should have done this one first actually. Never mind. This lambda is the magnitude, so it's how many of these we're adding on, so the principle is exactly the same. This b, however, is the parallel vector, which is sort of what we were saying here. X doesn't change, so it's a parallel vector, so it doesn't change, because we're not having this blue line doing all that and going crazy. It's parallel. It always parallel, so the vector doesn't change. It can't change because it has to be parallel. Okay. Hopefully, as I said, that makes some kind of sense. It's a bit of a mess on the board. Never mind. So that's the equation r equals a plus lambda b. Okay, so as I said, hopefully you've got that. That was equation of a line there for vectors, because that's what we call. We could come up with that. There's no formulas like y r take r1 equals ax plus b or whatnot. There's nothing like that. You just have to be able to think of it in this kind of manner. Okay, so as I said, hopefully that was nice and easy. We're going to be going on to finding the angle between vector lines now. So we understand what a vector line is. Now, to understand what the angle is, we need to think of, okay, well, what was the angle that we came up with before between vectors? Now, this is not vector. This is vectors, not vector lines. Different thing. We said cos theta equals a dot b, a times b, over the magnitude of a times the magnitude of b. And AB, where AB was A1, B1 plus A2, B2, etc., etc. So that was for something where we had the vector like 3i plus 2j, for example, against the vector of 2i plus 1j. I've wrote I twice in my mind. And we always said this theta was the angle that the vectors were pulling out from. So the principle of that stays exactly the same. That's where the angle comes out from. However, we need to consider this in terms of vector angles. Because that was just sort of recap on a recap. Get good at these recaps. I think we need to do on the recap. Okay, just get what we're doing a recap on now. So, say we've got two lines here. So these are two vector lines. This is different because we have vector lines. So we'll call this L1. We've been practicing these lines forever. And we'll call this L2. We'll say where L1... I've got to say this one meal. L1, L2. We'll put it in vector line format. So we'll say L1 is where R, vector R, is equal to, we'll call this. So remember, the first bit is the vector that doesn't change, the constant vector. So we'll call this, because we're doing base vectors, we'll do it in 3D unit base. Or you could just do it in unit column vectors, whichever you want. I'll do it in column. So that's 4, 5, minus 1, plus lambda, 2, 3, 1, and line 2, which is the one going down, its R is equal to 3 minus 3 plus 2. Yeah, sorry, thinking of something else. I'm getting ahead of myself. minus 3, 2, 1 plus, I'm going to denote by the mu sign, u with a weird extension on it, and then that's 3, 1, 0. 3, 2, 1. This might not work out by the way, but never mind. So, what we said, in the same way that x might be 0, because this is the same way, remember we said sort of, that is almost the same as y equals c plus mx. So when we want the solution, we make this equal to 0. This sort of the x equal to 0 really. So we're just left with this c. Now when the solution is at 0, we're actually saying it's going from 0 to r. Okay? So therefore we have to add in this 0, 0 thing. So 0, 0, assume is there. And we'll draw a line going up to L2. And we'll draw a line going up to L1. Okay, because we're going up from 0, 0, just as we had before when we had that, I'll my luck to pick up a black pen again. Anything about that, I was just stating the fact that I picked up a black pen. Because, you know, there's a diagram there in black and I made a mess of that again. Right. So when we said we had something like that, and we said okay, we always have to start from A, going up from the origin. And when we said A was something like 3i plus 2j and whatnot, we'd always have to start from there, and then we'd add on the bit going left or right, depending if we were going up. But to get to this point here, so to get to the point where we're on the line, we have to get to one of these 2 points here. Now to get to one of these 2 points, in the same point as getting to where we're touching this line here, what we did was we took the initial bit, so we took that initial, we took the initial bit there and there. We said that initial bit was just getting to the line. So because this is the 0, 0, that bit there is the same as that bit there. So we're trying to get from this bit to the actual line. So we're trying to get from the origin to the actual 2 lines, because that's what we're interested in. Because when we get to these 2 lines, then we can consider the extra bit, the parallel vector. But we're not at the line yet because we're at 0, 0. So to get to each line, we have to use the starting bit to get to the line from each one of these equations, because it's different for each one. Okay, so to get from 0, 0 to the L2, so we have to look at the L2 equation. Now the L2 equation has the starting vector of this, minus 3, 2, 1. So therefore, this from 0, 0 to L2 is minus 3 plus 2, 1. Or minus 3 plus 2 plus 1. So therefore, because it's 0 to the line, 0 to L2, therefore, the point, because we're going from 0, so any move we make in the vector, the path of the vector, will end up being a coordinate. So therefore, this is a coordinate of that point. In the same way that for L1, to get from 0, 0 to L1, then we have to use this bit here of the line. So therefore, it's 4, 5, minus 1. So to get to that point, it's 4, 5, minus 1. Therefore, the coordinate of that point, such as there, but in this case, it's here, is 4, 5, minus 1. Okay, so that's very good. But what we're assuming, we can sort of assume, is that we sort of have this y-axis somewhere on here. Okay. So we could almost say that for L2, for L2, we could almost have this as being. Oh no, actually that's not going to work. Best to explain this actually. Okay, so to get to each one, so say for L1, we had the y-axis as up here. Okay, so for L1 we can imagine this is the y-axis, and this is a scenario for L1 where we've got a line, instead of going up like this, in fact redraw that actually. Just put that down. So for the context of L1, so say this is the line, but in L1 we're going to redraw the line, but on the y and x axis instead of this weird shape down here. So if you were to draw this, just L1 on the x axis and the y axis, it would look something like this, where you would have that, and then yes, that's L1. Okay, so therefore we'd say this point that we're focusing on here is somewhere like this. Okay, so to get from the origin to the line, so to get from the origin to the line is the same as going from so to go from the origin to the line, we're going on this direction here. So we're going 4, 5, minus 1. So therefore, this little black bit going up to the blue line, that's 4, 5, minus 1. Okay, so the point there is 4, 5, minus 1. Now that's not right, because that actually should be in front of the y-axis really, because that's saying 4 to the right. But we'll just assume my maths inaccuracies is a bit underwhelming here. yeah, you can sort of imagine. I know that's mathematically incorrect, but this is, you can imagine it like this. So therefore, one vector along this line is, say if we had a magnitude of 1 and we wanted to go along this line by a magnitude of 1. We said this is the magnitude m. Okay, so the magnitude of 1. So if we assume x to be 1, which is this lambda thing, if we assume the x to be 1, then we will, sorry, if we assume the magnitude to be 1, then we'll get this x value at 2, 3, 1. So therefore, one vector along this L-axis is going to be 2, 3, 1. And because we're in this part, we're considering the unit base vectors, we're going to go along this line by 1. So therefore, we have a magnitude of 1 unit base vector, so this is going to be 2, 3, 1. Okay, so if we apply the same theory, but to L2, so to get from the origin to the line L2, such as the origin to the line in L1, we're going to use the initial part. So that's minus 3, 2, 1, yes? But to have a magnitude of 1 along the line, such as we had a magnitude of 1 along the line here, we've already got this bit. So we're already on the line, we don't really need to consider the initial bit. We need to consider this extra bit on the end here. So we've got the magnitude. Now I'm going to assume the magnitude is 1, so we've got this x-axis here. It's 3, 2, 1. So therefore, because the magnitude is 1, therefore the x value across, or whatever, is going to be 3, 2, 1. So that's going to be the unit base vector along there. It's going to be 3, 2, 1. Okay, so what we can deduce from this, therefore, is the angle, because these two are pulling each other away. These are the actual vectors now. But these were just lines getting to the vector, so we can sort of ignore this bit. So therefore, the angle that we're measuring between is these two vectors that are pulling away from each other, the vector lines. So therefore, our theta is going to be in there. So the two vectors we're considering are these two, the 2, 3, 1, and the 3, 2, 1. So therefore, the two vectors that we're considering are the two end ones up here. So it's the two additional vectors that we're considering, really. Okay. So we do the same principle where you do the square root of both of them to find. Sorry, no, not square root. So you do cos theta equals the a dot b, or a times b, over the magnitude of a times the magnitude of b. So you just apply that case to these. Okay. So we said a1 times b1 plus a2 times c2, etc. So what you'd end up doing, to cut it short, with 2 times 3, which is 6, I just put 2 times 3, which is 6, 3 times 2, which is 6 again, 3 times 2, and then 1 times 1, which is obviously 1 times 1. So that's a dot b, and then you do the square root of 2 squared plus 3 squared plus 1 squared times the square root of 3 squared plus 2 squared plus 1 squared, and you do that over this answer. Basically, you've got 2i, a is equal to 2i plus 3j plus k, and then b is 3i plus 2j plus k, and you just apply that idea of what we did before in terms of finding out the angles, but because you just have to do this extra bit of working out there. So as I said, hopefully that's some kind of help to you. What we're going to move on to now is we're going to move on to parallel vectors, which is sort of more complicated, but it's quite interesting. So we're going to be moving on now to something we call parallel lines. So I've put two equations of two different lines, vector lines, on the board here. Now don't get worried at the moment initially for this 3a, 2a minus 1b. And on this side, a 2a minus 115. They're just constants. But I'll explain a little bit why I've put them in, because we're going to be doing a question on these two lines. But I just wanted to obviously go over a few things first. Now, when we were saying to think about parallel lines, we have to think about perpendicular. So it become obvious. So perpendicular lines, we said when we had perpendicular lines of normal vectors, they were in a different ratio. So if one didn't have any a's in it, for example, the other wouldn't have any a's in it as well. So therefore parallel lines are going to be in the same ratio. So, so basically, this bit over the parallel line, so the initial vector that we called it, that is irrelevant because we said, if you remember, that was basically essentially getting from the origin to the line. So we can sort of really ignore that. So therefore, the only bits we're going to be interested in, because the parallel lines, so they're going to have the same gradient. So it's just how far along the point we're looking at. So therefore, all we're going to be really interested in is, sort of, is this part where it's lambda 3a 2a minus 1b. This lambda is just saying, okay, this is the parallel vector, really, and the magnitude along it. But really what we're interested in is these column vectors, so where I've put the non-integer powers, so the 3a, 2a minus 1b, and say for this side sort of thing. So we're going to only be interested in them things. Okay, so basically, there's no other way of putting this really. So there is a constant, and we're going to call this constant k, times the first parallel vector. So in this case, 3a, 2a minus 1, and b. And that is equal to the parallel of the second vector line. So that is equal to bracket a, 2a minus 1, 15. So they are equal. And we have to use that information to be able to find the values of a, and b. Obviously, we'll find k in the process. This k is just a constant. I could have quite easily written z or anything. Just probably apart from lambda or mu or r, but you know, anything that would make logical sense, say that's the constant, we could have that in there. So what we're actually going to do now is actually going to kind of confuse you, because what it's essentially saying is k times 3a is equal to a, or k times 2a take 1 is equal to 2a. So call that 3a take 2. Did this in my answer as well. Is equal to 3a take 2. Okay, and then you'd go on, but really, we're only considering the a's. We're trying to find out the a's. And seeing as the a's are in the I and j columns there of the column vector, then we're only going to be considering them. And we're going to be using our answers of what we find out of a to be able to find out b. Okay, but now what you'd expect us to do from that is go, well, k is equal to a over 3a. Well, not really, because, well, it is, but we're looking at the ratio, remember, so we're not really bothered about this constant k. So what we're just going to do is going to do the 3a over the a, because that, we could do, I suppose, because of the same value, so to get from 3a to a, to get from 3a to a, you're going to have to times it by something k, and that is going to get exactly the same number as going from 2a to 3a take 2. In terms of working out when you worked out what a actually is, you're going to get the same, you're going to have to times it by something similar. So if you were to go backwards, so if you were to go from 3a to 3a and 3a take 2 to 2a take 1, you'd be timesing it by the same figure as going from a to 3a and 3a take 2 to 2a take 1. So, but I'm just going to be awkward and go backwards. So it's going to be a. So one sec. Just make sure I do this right. Yeah. So I'm going to do 3a over a, and that's going to give me a constant. In this case, whatever it would be here. And then I'm going to do that is equal to 2a take 1 over 3a take 2. Now we're going to do it from here as generally as we would if we were solving a sort of rather basic equation. Times both sides by a and times both sides by 3a take 2. So when we simplify that down, it's going to get us 3a times 3a take 2. And that's going to give us an answer which is equal to 2a take 1 times a. So if we expand this out, so that it gets us 9a squared take 6a, and that's equal to 2a squared, take a. Simplify this down, because looks like we're going to get it in the form of a quadratic. So therefore, bring the 2a across, that gets us 7a squared. Add a to both sides, that gets us minus 5a equals 0. Now, normally, because this is a question I've just come up with, I'll explain why it might not work, but the method is exactly the same. You probably would get a proper quadratic, so you'd have 7a squared take 5a plus 3 or something. But you could get something like this, so this is entirely possible. So if you've got a quadratic like this that didn't have a number on the end, one way of doing it would be to take out common factor, so that you take out a, so that would be 7a take 5 equals 0. So therefore you get two values for a. So you say, oh, well, either a equals 0 or a equals 5/7. Okay? So what you'd do then is you'd go, right, well, we know our values for a either is 0 or 5/7. So we need to use that knowledge to be able to find what k is. Okay, so we're using these two formulas up here. So if we say, okay, well, k times 3a equals a. So k times 3a, so we're going to start with 0. So k times 3 times 0 is 0 equals 0. Therefore, k equals 0. Yeah, this is why it wouldn't work naturally. If this was a real question, and you put either one of these values into doing k times 3a equals a, you'd get the same value for k whether you put one found value for a or your other found value for a. However, because as I said, this is a made-up question, it doesn't work, but the principle is exactly the same. So you'd work out the value for k by using one of your a values. And then you know what the value for k is? I'm just going to assume it isn't 0 because it's going to give us a bad answer. I'm going to assume we're going to use 5/7 actually. So k times 3 over 5/7, so that's 15 over 7 equals 5 over 7 times both sides by 7. So 15k is equal to 5, therefore k is equal to 3. That's a lot nicer. As I said, in a real question, when you put what your value for a in to k times 3a equals a, then you would get exactly the same answer for k. But as I said, this is a made up question, so I'm just being awkward and trying to confuse you on purpose, see if you're paying attention. And obviously, if you subbed your value for a into this equation as well, which is a lot longer, I'd always go for the shorter one because I'm lazy, as you can tell. So, as I said, we'll give you the same answer for k, whichever equation or whichever value of a that you found out you used. Otherwise, you'd know you've done it wrong somewhere. However, because as I said, I made a question, and I just like to be awkward, I know I've got it wrong, so... I know I've got it right, because I'm a genius. So, anyway, so we know the value for k is 3. So, we can rewrite this as being 3 times 3a equals a, or 3 times 2a take 1 equals 3a take 2, or 3 times b equals 15. Now, we know what a is, so we don't need to put it into the first two. So, we need to put it into the second one. So, therefore, 3 times some value, b, is equal to 15. So therefore, b is equal to 15 over 3, therefore b is equal to 5. Now as I said, it would change if you use 0, but that's the method you would use, okay? So now we've found values for a and values for b, and that's all the question was asking in this case, saying, given that these two lines are parallel, find out the values of a and b, which we have done. As I said, it would work for either of these two equations, finding, you know, at this stage we can put a is 0, a is 5/7 into either one of these equations, should get you the exact same value for k. So we've got these equations from doing, this was initially k, so we said k times 3a equals a, and k times 2a take 1 equals 3a take 2. Now, just to recap, when we did here, we did 3a over a is equal to 2a take 1 over 3a take 2. We could have easily done a over 3a equals 3a take 2 over 2a take 1. Could we? Now, I think it's good to do it this way actually, because this is the way most teachers like to teach it. So I actually don't want to confuse you even more. So basically, even though really it's saying k times 3a equals a, because k affects the ratios of, we need to work out the ratio between these two to be able to work out the values for a. So we said 3a over a equals 2a take 1 over 3a take 2. Okay? And then simplified it down, worked out the value for a, and then put it back in, because this was, as I said, initially k, so k times b equals 15, and simplified it from there and got a value for b, and therefore that's what you'd work out. Now, it may say in the exam, like, if this was a proper question, I would say a is greater than 0, otherwise you'd have a problem using that one. Okay. Alright, so that's one way to do that. So yeah. So as I said, I'll be doing some proper questions in another video, but I just was quite lazy today. Couldn't be bothered to put any in. So thanks for watching. As I said, hope it's been some kind of help. I'll just zoom in if you couldn't see that before. So thanks for watching, and we'll see you in the next video.